In this video, we're going to talk about arrangements with repeats. Now, we've talked about arrangements previously in a previous video, and that was when you would have like 10 things and you want to figure out how many ways you can arrange them in a line. So, for example, how many ways can you park 10 cars in a 10-car garage? That sort of question. Well, arrangements with repeats follows along in that line, except with repeats, what we mean by that is there's something in it that's indistinguishable. In this video, I don't only want to just tell you the rule on how to calculate arrangements with repeats. I want to explain why that rule is what it is, and it takes a bit of time to unpack, but if you can see the why behind it, it'll help you remember it, and then we're going to build on this concept in later videos with other counting techniques. So it's important to understand the whys of what's going on. So for example, let's say I have the name Anne and I want to talk about how many different ways can I rearrange the letters in Anne. Well, because the two N's are essentially the same, it adjusts how many ways you can do that. For example, if I just switch these two N's, that would still be ANN. Now, if we just went by our strict rules of how we learned how to count how many arrangements there are in the previous video, then those would be counted as different arrangements, but in reality they're the same. So we need to come up with a way to account for that over-counting. The name ANN is a little too simple to see the pattern of what's going on, so I'm just going to throw another N on there, and we're going to look at the different ways of arranging ANNN in just different orders. So for example, I could switch it so that the A was second, and that would be a different arrangement. However, if I switch just these two N's here, that gives me NANN, and these two guys are the same arrangements, even though we switched letters. So we've got to figure out what to do about that. And in order to do that, what I'm going to do is a couple things. First of all, I'm going to give the N's subscripts so that we can distinguish them from each other. In reality, there is no distinguishing them, but we need to distinguish them in order to figure out the pattern of what's going on when we do all the arrangements. So I'm going to use subscripts to do that. All right, so now with the subscripts in place, we can look at some arrangements and see what's going on. So I can keep the A in place, I can keep the N1 in place, and once those two things are decided, I could switch the N2 and the N3. And so I get two different situations that basically account for the same thing. Now I could do this idea and I could keep I could make N2 be the second guy. And then with N2 in the second slot, then I could decide, does N1 come next or does N2 come next? Once I decide that N1 comes next, that forces that last guy to be N3. But of course, I could have chosen to put the N3 and then N1. Okay, so what I'm going to do, hopefully you're seeing kind of the pattern for mapping this all out, but what we've done so far is we've listed 4 different ways of arranging these letters that are all essentially the same ways. The subscripts are just helping us keep track of what we've done. So I'm going to go ahead and list all these out. Now this can be visually overwhelming, so don't let it take you back too much. The idea is to look at the patterns in it, and so you can just kind of step back and take it in instead of trying to write it all out or anything. Take in what I'm saying as far as exploiting the patterns. Okay, so here are all the possibilities of these 4 letters being arranged in different ways. And then, like I already admitted, it's a bit visually overwhelming, but what I've tried to organize it here so that this first column, all the A's are first. Those are all the options with A's first. The second column are all the options with N1 first, and then N2 first is in the third column, N3 first is in the third column. Now, also with that, I want to remind you what we learned from the previous video about arrangements in general. We have 4 things here, so there are 4 factorial ways of arranging those, which equals 24. And that's what we have here, is a list of 24 different arrangements. But if you look at these, well, first of all, this first set where A is first, all of those are essentially the same. So if we're counting how many ones they are where we don't overcount the repeats, that all counts as one thing. And then if you look, the rest of it's a bit scrambled, but we could find it. It's just organized a little differently. It's not all in a column, but if you look here, all of these are the ones that follow the pattern NaNN. The next little section here, these are all the ones that follow the pattern NNAN, and then this last section follows the pattern NNNA. So we definitely see a pattern in here. If you look, each highlighted group has 6 items in it. So we can figure out that the good thing about that is since there's a pattern there, we can find a mathematical way to calculate how many that would be without listing them out and literally counting them. Just to make sure we're all on the same page with this, I'm going to take a slight diversion here and explain some stuff so that you guys can better see the mathematics that we'll use to figure out how many is going on here without counting it all. The diversion I want to talk about is division and what's going on with division. Now there's different ways that division can be conceptualized. They all kind of amount to the same thing, but one way is using this idea that we are breaking things into groups. Now if I break this into groups of 3, so I'm going to just draw some red lines here to indicate that, then there's 2 things in each group. Now I could say that this represents 6 divided by 2, which equals 3. So the idea that since there are 2 things in each group, we're going to end up with 3 groups. This number here is telling us how many things are in each group. And then this number here tells us how many groups we end up with. So for example, if we divide it into 2 groups, that's telling us that 6 divided by 3 is 2. So if we put 3 things in each group, that results in 2 groups. And then if I do 6 divided by 6, that equals 1, which means if I put 6 things in a group, I end up with 1 group. I want to go back to the notion of 3 groups. So if I divide it into 3 groups, there are 2 things in each group, but essentially what we're saying with those is that these 2 things are the same, so we're not going to count them any different anymore. There's just one thing there. We're counting them based on the number of groups instead of the individual actors in the group. There's 1 there, even though there's 2 in the group, there's 1 there. So division is, in a sense, is this idea of dividing things up into classifications and then just handling the numeration by how many classifications you have. With this notion, let's go back to our arrangements with repeats. Okay, so now that we've looked at that construction for division, we can look here and see that what we've done is taken our 24 items and divided them into groups where there are 6 things in each group. So we have that 24 divided by 6 equals 4. And so if we're looking at how many total arrangements there are of ANNN, there's actually only 4, because they get classified into, even though there are 24, they get classified into 4 groups where everything in that group is essentially the same thing. Now, what we need to hone in on here is this 6. That 6 is the magic number we need to figure out. We already know how to figure out the 24. That's 4 factorial. That's the total number of arrangements if they're all distinct. But then we need to take that total and divide it by, in this case it's 6, to determine how many unique arrangements there are. Well, where did that 6 come from? And to talk about where that 6 came from, I'm going to just focus on my yellow box there. I'm going to clear out the rest of the screen, and we're going to focus on what's going on in the yellow box, because it's going to be the same pattern for each one of the boxes. Okay, so again, we know we have 24 total items when we listed them all out, but if we group those based on which ones are actually the same, we end up with 6 in each group, which leaves us with 4 groups. So what we're trying to figure out is, what is this 6 about? Because if I understand in general what the 6 is about, then I can apply that pattern to any problem. Well, if you look here on our arrangements that I left up, essentially all the variations, because the A stayed put, so all the variations are the different placements I have for my 3 ends. Well, what we saw with arrangements, if I have 3 things, I have 3 choices for what goes in the first slot, and we can literally see those there. I could choose an N1, I could choose an N2, and I can choose an N3. Now, once I decide on one of those choices, let's say I decide on N1, then I have 2 choices for what goes in my second slot, and I can see those there. If N1 is first, then N2 can be second, and N3 can be third. Now, once I decide on one of those, say I choose N2, then that forces my last option. I only have one option for the last guy. And this is, we multiplied that up, and that's where we got the idea that to arrange 3 things is 3 factorial. But it's not coincidental that that equals 6. That's that magic number. We're trying to figure out where it came from. And basically, it came from the number of ways of arranging all of the things that are identical. So in this case, we're arranging 3 things, and so there are going to be 6 different arrangements of those identical twins, identical triplets, there we go, that will account what will end up being all the exact same thing. So that is really the big thing that I'm trying to convince you guys of, that the number of identical arrangements when you're doing arrangements with repeats will be the number of repeats factorial. Let me write that out for you. All right, so again, the number of arrangements that will be the same when arranging items with repeats is the number of repeats factorial, period. So what that means is, if that tells us the number of repeats, then we can, again, divide by that number to determine the number of actual unique arrangements we have. Let me write that out, because that's the big rule. So to determine the number of unique arrangements, we divide by the number of repeats factorial, period. All right, and that's what we saw up above here, where I have this 24 divided by 6 written out. What the 24 was the 4 factorial of the total number of ways I can arrange 4 items. But then we divided by 6, but what the 6 was 3 factorial. That's the number of repeats factorial. And that gives me 24 divided by 6, which is where my 4 groups come from, or my 4 classes of arrangements that were all essentially the same. So take a second, make sure you're seeing what I'm talking about with this pattern. What we're going to turn to next is to do a couple of examples where we're going to use this rule to figure out how many arrangements we have when some of the elements are repeats. Okay, so how many ways can we arrange the digits of this really big number? Okay, so here we first want to determine how many numbers we have. We're going to have 10 digits there. And so that would be 10 factorial. There are 10 factorial ways to arrange those 10 digits. But now we have to consider whether or not we have repeats. So for example, if I switch this one and this one, I have the same number. It's indistinguishable. So that would count as a repeat. In total, we have 4 ones that are repeated. And so that means that we need to divide our 10 factorial by 4 factorial in order to determine the total number of arrangements that are all distinct from each other. So when I do the math out on that, I get 151,200. So there are that many ways to arrange that. Let's look at a slightly more complicated example. How many ways can we arrange the letters of the word Mississippi? So the reason why this one's a slightly more complicated example is we have repeated i's, we have 4 of those, we have repeated s's, we have 4 of those, and we have repeated p's, we have 2 of those. Only the m is unique. So first of all, we need to figure out how many total letters we have. There are 11 total letters, so there's going to be 11 factorial total ways of arranging these if they were all distinct. But now what we do with the repeats is we're going to divide out their factorial. So every time I move s's around for other s's, there's going to be 4 factorial ways I can rearrange my s's. Same thing with the i's. There are 4 factorial ways that I can rearrange my i's. And with my p's, there are 2 factorial ways that I can switch my p's around with themselves. And so for every repeat, you're going to divide out that number factorial because there's going to be that many ways that we can rearrange that identical twin with itself or identical triplet with itself or so on. Now, as far as how all these options go together in the denominator, we're just going to use our fundamental counting principle, which tells us to multiply up all the different options. And so there you have it. That's how many different ways to arrange Mississippi. We just now have to calculate it out to figure out what that actually is. With some handy-dandy calculator work, I get that there are 34,650 of those different arrangements. Alright, so go ahead and give some of these a try and see how you fare.